All right, let's dive in. We're about to talk about a technology that doesn't just improve on what we have, it completely rewrites the rules. We're talking about harnessing the strange, bizarre, and unbelievably powerful laws of quantum mechanics to build a new kind of computer. This is a leap so big it could change, well, pretty much everything. So, let's get into it. So, think about this for a second. Every single piece of technology you use, I'm talking your phone, your laptop, the entire internet, it's all built on a very simple idea. Bits of information that are either a 0 or a 1, off or on. That's it. But what if we could just throw that rule out the window? What if the basic building block of a computer could be both 0 and 1 at the exact same time? That very question is the key that unlocks the door to the quantum realm. To really get a handle on this revolution, you've got to start with the absolute basics. We're talking about the fundamental jump from the bits we've used for a century to these new, strange things called quantum bits, or qubits. And here it is, the main event. A classical bit, it's like a light switch. It's on or it's off, a 1 or a 0. Simple. A quantum bit, what we call a qubit, is totally different. It's more like a dimmer switch. It can be fully off, so that's a 0. It can be fully on, a 1, but it can also be any possible value in between, all at once. And that ability, the power to be in multiple states at the same time, is what opens up a whole new universe of computing power. It lets you explore a massive number of possibilities, all in parallel. Now, okay, I know what you're thinking. You see an equation and your eyes might start to glaze over. But stick with me. You don't need to be a physicist here. All this equation is really saying is that the qubit state, that's the psi k, is a mix, a combination of both 0 and 1. Those little c numbers just tell you the odds, the probability that you'll find it as a 0 or a 1 when you finally look at it. It's not an answer. It's a recipe for all the possibilities. So how is any of this even possible? Where do qubits get these wild abilities? Well, it all boils down to two concepts from quantum mechanics that are, frankly, mind-bending. Let's call them a qubit's superpowers: superposition and entanglement. Superposition is that whole being in two places at once idea we just talked about. The best way to think about it is to imagine a spinning coin. While it's spinning in the air, is it heads or tails? Well, it's kind of neither, or you could say it's in a state of being both. It's only when the coin hits the table, when we measure the qubit, that it has to pick a side and land on either heads or tails, a 0 or a 1. Okay, so if you thought superposition was a little weird, you might want to buckle up, because entanglement is where things get truly bizarre. Einstein himself famously called it spooky action at a distance. Imagine you have two of these quantum qubits, and you entangle them. They are now linked. Their fates are intertwined forever. If you check on one and find out its state, you instantly know the state of the other one. And here's the crazy part. It doesn't matter how far apart they are. They could be in the same lab or on opposite sides of the galaxy. It's an instantaneous connection. And I really want you to let that sink in. This isn't just a fun thought experiment. As this quote says, the effect is instantaneous across millions of light years. It completely breaks our everyday understanding of how space and time are supposed to work. But it's real, and being able to harness this spooky instantaneous link is one of the absolute keys to unlocking a quantum computer's power. So, let's recap. You've got these qubits that can be a mix of 0 and 1, and you can link them together in these spooky instantaneous ways. So what? What's the point? Well, this is where it all comes together. This allows us to build brand new kinds of algorithms that can solve problems that are literally impossible for even the fastest supercomputers we have today, or ever will have. And the impact of this is just staggering. We're talking about the ability to discover new medicines and materials by perfectly simulating molecules. We could revolutionize AI and financial modeling. We could search gigantic databases in the blink of an eye. But the one that always gets the headlines, the most famous and maybe infamous use, is its power to break the encryption that keeps our entire digital world safe. Yeah, this is the one that keeps security experts up at night. There's an algorithm called Shor's algorithm, and it's perfectly designed for a quantum computer. It can figure out the prime factors of a huge number, which sounds boring, right? But here's the thing. All of modern encryption, the stuff that protects your bank account, your emails, your passwords, it all relies on the fact that this problem is ridiculously hard for regular computers. For a quantum computer running Shor's, it's easy. It could basically hold the master key to our digital lives. But here's the twist. This incredible power to break codes also gives us an incredible power to create them. But getting there is filled with some of the hardest engineering challenges imaginable. So let's talk about the two sides of this coin, the amazing promise and the serious peril of the quantum frontier. And this really lays it out perfectly. On the one hand, you have the promise of things like quantum cryptography. We could build communication systems that are fundamentally unhackable, guaranteed secure by the laws of physics itself. But on the other hand, there's the peril. The huge roadblock, the Achilles heel of all quantum computing, is something called decoherence. So what is decoherence? Well, to put it simply, these quantum states are unbelievably fragile. Think of it like trying to do a complicated calculation during an earthquake. The slightest vibration, a tiny change in temperature, any little bit of noise from the outside world can make a qubit lose its quantum magic and just collapse back to a boring old 0 or 1. The entire calculation is ruined. So the biggest challenge right now is just figuring out how to build a machine that's perfectly, and I mean perfectly, isolated from the rest of the universe while it's doing its work. And that really brings us to the ultimate question, doesn't it? The race is on. Labs all over the world are pushing the boundaries, trying to build bigger and more stable quantum machines. We are standing right on the edge of a new era of computing. But success isn't a given. It's a huge gamble. We are trying to tame the fundamental building blocks of reality itself, a world that is both more powerful than we can imagine and more delicate than we can comprehend. The question is, will we get there?